Alright, I should probably stop that now. We're going to do some math. Hello, everybody. Okay, so the goal of today's video is just to introduce us to some mathematical equations that we consider to be non-linear systems of differential equations. And rather than kind of going like with the pure form here, I want to show you some examples and just talk about them a little bit without getting too deep into the analysis. I'll show you some things. But then in the next couple of videos, we'll actually go through a lot of the work that needs to be done in order to, I don't know, basically understand them a little bit better. Where the hell is my mouse? There it is. Okay. iPad. Well, there we go. Okay. I've already got an errant mark right there. Okay. I made this little box so I didn't draw on it. It's important. Okay. All these examples are going to be from biology just because they're a bit easier and they don't rely on like people having knowledge of physics. I don't need this anymore. Because we can just sort of like talk our way around them and get to know them. All right. The first thing I want to do is I want to build for you guys the basic SIR model. Okay, SIR model. This is the standard epidemiological model that is sort of the building blocks that a lot of us can go on to do more and more complicated things with after. Okay, so the SIR, this is an example of what's called a compartmental model. And basically what you're doing is you're taking your whole population, and you're dividing it up into 3 compartments, okay? And these compartments are basically what kind of epidemiological status they are in, okay? The first one is susceptible to the disease, which means these folks can get it, maybe haven't gotten it before or whatever. These are infected, and most importantly, not only are infected, they are infectious. Okay, and then these folks are recovered, and we consider them for this case, for this sort of relatively simple case, to be immune to the disease once they've recovered. Okay, so I'm just going to label this box S, I'm going to label this box I, and I'm going to label this box R, and we see where the name SIR comes from. Okay, and then folks, when they get infected with the disease, they can no longer be susceptible, but they basically transition into the infectious class. Makes sense, right? And then after being infectious or infected for a while, you do recover, and so we go to R. Now, there's a lot of other complicated things that could go on in diseases, a lot more stages, a lot more like loss of immunity or things like that. But for now, this is what we're going to stick with, okay? Now, if we want to talk about equations for the SIR model, I want to basically make up a little story, okay? So let's say, let's do some colors. All right, healthy, let's go ahead and make that blue. Infectious, let's make that green because they're sick. And then recovered, we'll make that red. Red, something a bit different, okay? So let's say you are a susceptible individual, okay? So you're sitting out here all nice and happy, okay? Okay, and every day you have a certain number of contacts you're going to make. Okay, let's call that contact number C, which we will just for now say number of contacts. Now, I want you to know that the way I'm deriving this model right now is technically wrong, and that's fine. This is enough to build some intuition. If you take my Math 315 course, we'll build it in a much more sophisticated manner, okay? Now, who you're allowed to contact is basically, in this idealized case, everybody in the world, okay? So if I took all these susceptibles plus all the infected and plus all the recovereds, that would give me my total population. Let's go ahead and call that N, the number of people, okay? And for now, while these SI and R can all be functions of time, we're going to suppose N is constant, okay? So we've got just a whole bunch of other folks in the world. Okay, so I'm just drawing a whole bunch of circles. Okay, and now the thing with this is that some of these guys are going to be also susceptible. Go ahead and do that. Some of them are going to be infectious because they're sick. All right, and some of them will be recovered. Okay. And now we are going to have to make C contacts. Just for right now, let's go ahead and make C, let's see, like 3. C equals 3. Okay. And then when we sample from these people that we come in contact with random, okay, I might make contact with this guy. Oh, yay. I might make contact with that guy. Oh, yay. And I might make contact with that guy. Oh, yay. Hey, there's no chance of me getting sick in this scenario because I happened to have chose 3 susceptible people at random, okay? But it's very possible, like on the next day when I go make contacts, I might, make contact with you again. That's nice. But instead of that susceptible person, I might make contact with this infectious individual. Oh, and I might make contact with 2 infectious individuals, okay? Now, since we're sampling all these at random, I want to know sort of what's the probability of coming in contact with an infectious individual. All right, and so in this case where I wrote down, how many folks do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 folks. All right, so N is 18 in this case, in this situation. And I have 1, 2, 3, 4, 5 infectious individuals. So the probability that I reach out and touch an infectious individual at any given time is 5 over 18 in this case, which is around 1/3, 1/4, okay? It's bad, but it's not too bad, okay? But then we can talk about our expected number of infectious contacts that I make in a day. So if I'm making 3 samples of this population, and this is my probability of coming in contact with an infectious individual, then 3 times 5 over 18 will be my sort of expected number of infectious contacts. And if you can see, that's really close to 1 in this case. So things start to get a little scarier. Okay. Now, just because I make contact with an infectious individual, that doesn't necessarily mean I get sick. Something has to happen, right? There's got to be basically like, there has to be a chance that these viruses that come at me, that I don't get sick. Okay. We're going to let that probability, so probability of infection given infectious contact, we're going to let that be rho. It's kind of like a P, but it's got a little tail and it doesn't close. Okay. So if I take a look at this here, I've got rho is the probability of infection given an infectious contact. And then I've got this sort of expected number of infectious contacts right here. So if I multiply all that together, I sort of get this, what's called the force of infection. All right, it's an amalgamation of my behavior, the number of contacts I'm making, prevalence of the disease, how many people are sick, and then the nature of the disease, like how infectious is it actually. Okay, so if I go ahead and let's make a master image here. Whoops, I gotta let go. Boop. 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 Did I leave myself enough space? Boop. No, I did not, but that's okay. We're just going to make very small arrows then. Actually, no, I want to make the arrows big and the boxes small. I'm sorry, guys. Please hold. Do 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 do. So I'm gonna make a compartment right here. I'm not even worried about them being perfect boxes anymore. Gonna make a compartment right there. I'm gonna make a compartment right there. This is R, this is I, this is S. So moving from S to I. Okay. We need to know my number of contacts. We need to multiply that by the density of infectious individuals in the population. And then we need to multiply that by that rho, that sort of probability that that contact actually results in a new illness. Okay. Now that was just for me, right? That was just for me or for you, that one smiley person. Okay. But how many smiley people are doing this? Every single person in S. Okay. So this little rate right here that we just wrote, okay, that's going to be multiplied by S because each individual is participating in this action. Sound good? Now, to tell the narrative of how to go from I to R, we are again going to keep it simplistic. And we're just going to say that after a particular amount of time, you recover. So there's a recovery rate, and we're going to call that gamma. All right. Now that's for you, but all I individuals are doing this. So that gamma there is going to be multiplied by I. And what we get when we consider this compartmental model and write it down in equations is the following. Okay. ds dt equals, now I'm going to write SC rho I over n. All right. Now I got to think about this. Is this going to be increasing my population or decreasing my population? It should be decreasing the number of susceptibles, right? So I've got a negative here. So again, to read this, it's the number of susceptible individuals multiplied by the contact volume that they participate in. In this case, I multiplied it by the probability that an infectious contact results in an infection, multiplied by the probability that one of their contacts is in fact infectious, given random mixing and all this fun stuff. Okay? Now, when we write our di dt equation, everybody who's moving from S moves into I. There's no loss, okay? It's not like in that fox and rabbit situation we did earlier where you lose some rabbits, but you don't gain that equal number of foxes here. When somebody gets ill, they move into the infectious class. No ands, ifs, or buts about it. So it adds, it's positive. But after a while, they might recover, and so we've got a negative rate right here, negative gamma I. Those are flowing outward into R. And so my recovered population in this model is just going to be changing according to gamma I. And so we've got three differential equations, which should already be like, whoa, 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 this is crazy. All right. And they are certainly nonlinear, as we can see right here. Let me just actually do this way. Go away. In this term right here, I've got an S times an I. And so I've got my state variables touching each other, so that automatically means it's nonlinear. Okay? Don't freak out that it's actually three-dimensional, because it is, in fact, two-dimensional. And so this comes into sort of how we can analyze some of these things. If I look at ds dt plus di dt plus dr dt, what do I get? I get 0. And so that means S plus I plus R should equal some constant. Oh, we've already labeled that constant n, right? To make this equation really show what's important, S of t plus I of t plus R of t, which are all quantities that are changing over time, equals some constant n, which is my total population. And so because of that, if I know, let's say S and I know how many folks are in the total population, then I can automatically figure out what R is, so I don't need the R equation. Furthermore, if I look at my differential equations, R never shows up on the right-hand sides, so I don't need it. So really, I just need to consider this pair of equations. Now, there's a lot of analysis that can go into this. I'm not going to get into it here in this video. But basically, the outcome of this model is as follows, and this should look familiar to any of you who are watching way too much news. Okay, on my vertical axis here, I've got time. All right, and on my that's my horizontal axis. On my vertical axis, I've got population. Okay, now what usually happens in these situations is we start out with a whole bunch of susceptible individuals. We start out with just a small amount of infection, something above 0, and we start out with no recovered individuals. So that should be at 0, but I don't have the sophistication, whatever. We're at 0 for R, okay? Now, what happens over time, if we look at the I equation, is that we've got this growth to a peak, and then it decays off with an exponential decay forever. Okay, to mirror that, what's happening to my susceptible individuals? Well, those are the ones feeding into that I equation. So they go down in a similar manner. And then what's happening to my recovered? Well, everybody who's infectious eventually becomes recovered. Don't make a straight line. Eventually becomes recovered, and we get something that looks like this. Okay, now, different analyses that can be done here. As this guy flattens off right here, this difference between where S started and where R ends, these are how many folks who avoided illness. This value right here, which we can think of as sort of like the limit as t goes to infinity of R of t, that's known as your final epidemic size. That's how many people got sick, which should be equivalent, if we think hard, as to the area under the green curve. Okay, This thing right here is known as this is our peak time of infection, and this is our peak level of infection. Okay, and there's all sorts of cool analysis, but this is the basic sort of outcomes that you can get. And we can do all of this with what we've already done with linear systems, just as an FYI. Okay, so there's an example right there. Another example of a nonlinear system that we have discussed in some detail are ecological, there's an A there, interactions. Okay, and the way I like to think of these things is the following. Okay, I've got some species X. Okay, so I've got dx dt, and species X, when he's all by himself, has some growth function, some g of x here that just he might be growing, might be exponential growth, might be exponential decay, might be logistic growth, whatever the case may be. Okay, but then there's another function here. Let's go ahead and write that with a capital I, which is a function of x and y, where they interact with another species. I don't know why I put minus, I mean plus. Another function there, where they're interacting with another species. And then that second species, dy dt, also changes, and they have their own function, g of y. I'm trying to write in cursive here. I don't know why I chose lowercase letters. Let me fix that to really drive it home that they're different. Here's g. There's g. Cool. And then they also have their own interaction function of how they interact with the other species. Okay. Now, what's interesting here is that there's a lot of different types of interactions that could create a lot of different dynamics. And depending on the individual growth functions, G and script G, we can have very different outcomes depending on what's going on. All right. But this leads us to basically a really cool chart and exercise that I'd like to go through with y'all. Okay. And there's a couple different ways to draw it. I'm going to draw it in my favorite way. Okay. So here's species X. Here's species Y. 1, 2, 3, 4, 5. And I technically need 6 spots, but that's okay. I don't need a whole cell for all of them. There we go. All right. We're going to go here. Each of our interactions here is going to have a name to classify them. And then what I'd like for you guys to do on your own, okay, is to think of examples. And I might come up with some right now, okay? Now, I'm going to use a plus sign for benefit. So they benefit from the interaction. I'm going to use a negative sign for harm. And I'm going to use a 0 for neutral. They just don't care. Okay, so let's start with both of them benefiting. Okay, when both of them benefit, this is called mutualism. Okay, and so this is where when the species actually interact with each other, they do better than if they weren't present. And I think a really good example here are plants and their pollinators. Okay, both gain a benefit from the interaction, and they would be worse off without the other. I think that's a good one right there. Okay. Now, the next one where one benefits and one is completely neutral. Okay, this is called, see if you know the word before I say it. There's usually like one person in class who knows it. Commensalism. I ran out of room. Did not leave myself enough space. Okay, and so to be true here in this, like what I've drawn right there, X needs to benefit from the presence of Y, and Y needs to not really care at all about the presence of X. And I think a fairly good example of this is remora and sharks. Remora are these little dudes that hook on to the side of the sharks and clean up, well, like eat the scraps that are coming out of the shark's mouth. And voila, the remora benefits, and the shark really doesn't care because he's big enough that he can carry all this weight. Okay. That's a good one there. X benefits and Y is harmed by it. This is called parasitism. But it need not be parasites. All right. We've already done an example of this with like foxes and hares, or predator, not predator, predator and prey. Right, where the predator loves the fact that his prey is around. The prey usually doesn't appreciate the presence of a predator. I could be wrong, but I don't think I am. All right, next one up. Let's do neutral and negative. Okay, so here X does not care about Y's presence, but Y is harmed by X's presence. Okay, this is called, whoops, I usually pronounce this wrong, and I'm invariably going to spell it wrong, so I apologize ahead of time. Amensalism. Amensalism? I don't know, I always get the word wrong. You can find it and figure it out, okay? This is usually modeled by extremely lopsided parasitism, where that benefit that one gets from the other is really negligible. But I think another good example are these ibex and a weevil. So the ibex and the weevil both eat the same grain. So this actually wouldn't be parasitism. It's going to be an example of one that we're going to do, two from now we're going to do, called antagonism. But the ibex and the weevil both eat the same grain, but the weevil eats so little that it doesn't really impact the ibex at all. The ibex eats so much that they can clear out the weevil's food source, so that they are harmed by that interaction. That's that. The next one is kind of a silly one called neutralism. They're just not affected. Finding this in reality, I don't know. First off, I don't know why you'd be modeling it, or secondly, I just think it's very difficult to actually not have an impact on one another's fitness. But you can think about like an elephant on the moon and a giraffe in New York City. Like, they just don't have any impact on one another. There are other things they have to worry about. And the last one is both negative. And this is called competition, but I'm going to call it antagonism because I love having isms everywhere. Okay. But I'm going to write right here, competing species. Competing species. And so this is where you both have the same prey, or you both want the same sort of territory, or even within a single species, individuals competing over mates or things like that. Okay, so we've got like these big tables and all these different sorts of interactions, and we can think about what that means. To do a specific example, I'm just going to kind of peek at what's going to be in the next video here. But basically, if I rewrite this dx/dt equals, whoops, hello, thanks for the needless scroll, appreciate that, I really don't, g of x plus I of xy and dy dt is the cursive letter version. Oh, it's tracking my palm because I'm now wearing my silly Michael Jackson glove. Okay. There we go. All right. So what's kind of curious here is like what sort of functions can go here and make sense? And truth be told, there's a lot of them. All right. If we talk about growth functions, so these big G's right here. Okay. Common ones are exponential. And these can be something like an exponential growth, an exponential decay, something like that. Or logistic is another common one, where we get something like 1 minus x over k. And if we kind of remember what these things look like, our exponential growth, whoops, looks like this. Exponential decay looks like that, right? That's not what exponential decay looks like. I'm having trouble drawing exponential decay. Cut me some slack. What logistic growth looks like is that there's some carrying capacity, K. And below it, we've got this S-shaped curve. And above it, we've got this exponential decay down. We did that one already. Once upon a time, all by itself, not in a system or anything like that. Other ones that are kind of interesting, I think, are... I'm stuttering. Ali functions. And so this is very similar, and I'm going to write it in a how do I want to say it? In a slightly different way to how everything's written over here. Okay. K minus x, x minus a. Okay. And we can make it look more like logistic by dividing out a k from the first one and dividing out an a from the second one. But this is always how I remember it, so it's a little bit easier for me. And in these, it's a bit different where there's a level A and there's a level K. If we start below A, whoops, we will go extinct. If we start above K, we'll crash down to K. And if we start in between, we will grow up to K. So A is this sort of like critical threshold that my population needs to be above, or else they'll go extinct. Like they just can't support their own population. So these are example growth functions, okay? I hope that gives us a little peek. For example, interaction functions, the most common one is a sort of mass action. And for those of you who are in chemistry, that should sound familiar. And in fact, the form of this should look incredibly familiar. It's A times X times Y. Or if I want to get with the chemists here, A, X, Y, or even if we're going to go nuts with it. Holy crap, look at that. All right, so it's simply the product of X and Y. So the more there is of either one, the more interactions are occurring. And the interactions are occurring at some rate A in this case, right? This is nice. It's straightforward. It's probably the easiest way to get a nonlinear interaction. Another one would be sort of like a standard incidence. Standard incidence. And these happen like AX times, whoops, Y over X plus Y. And so in this situation here, individuals from population X are encountering other individuals at random, sampled from the total population. And so the fraction of those that are with the other population is Y over X plus Y. Okay. This can also be changed to mass action if X and Y are restrained to be in 0, 1 for reasons that should be relatively clear. I'm sorry, my cat is doing something it's going to be doing. Psst. No, don't do that. Okay, I'm back. What was I talking about? Interaction terms, yes. There are also a bevy of these things called Hollings type interactions. And I'm not going to go over them in this video here, but I do encourage you to look them up. They are just basically other versions of stuff like this with squares and cubes and the whatnot, and the purposes behind them are explained within the relevant articles. Oops, I am behind the thing there. Anyway, thank you guys for tuning in to the pre-lecture. I'm going to do a more technical lecture now, okay? Where's the stop button?